By now we've seen many different forms of induction, and I'm hoping at this point you're realizing it's not a process which belongs to any one area of maths. It's actually more of a fundamental and quite elegant concept to do an induction proof. In fact, if you get down to how induction works, it turns out that it's actually mathematically equivalent to counting. Yes, it's that fundamental. Counting numbers equals induction. And it turns out that induction pops up all over maths beyond where we've explored it in this topic, and it's a good idea to practice some of these areas just for curveball questions. So for example, we see induction in complex numbers, Pascal's triangle, and even sets, which is one of the most fundamental concepts in maths. Today we're going to be proving this convex n-sided polygon thing, and the main reason that I want to look at this one is because it's really hard to tell what the question's asking just from the text. So what I'd recommend you do is watch me draw the picture of this situation and talk about what we're trying to prove, and then actually pause the video and try and do the proof yourself before you see the answer. Or if you think you can get it just with the text itself, have a go right now. But we'll make a start. So convex n-sided polygon means that we're not allowed to have, anything like that, because that would be like too big of an angle. Convex n-sided polygon might be like, I don't know, a square, a triangle, or like a pentagon, or something like that. And if you look at the square, you can see that it's got 2 diagonals. That triangle actually has 0 diagonals, because if I try and make one, I'll just be along an edge, not a diagonal. And this pentagon has, let's see, 1, 2, 3, 4, and 5. 5 diagonals. And so if we look at this, so here we'd have n equals 3. Here we'd have n equals 4. And here we would have n equals 5. And the formula actually does work. So for n equals 3, we can look at something like a half n bracket n take 3. And what we'll see is that becomes a half times 3 times 0, which is 0 diagonals, as we predicted. This one here, if we look at a half n take 3, that's going to be a half times 4 take 3 is 1. So that is 2 diagonals. So these are matching so far. If I look at a half n take 3 for the pentagon, then you've got a half times n is 5 in this situation, and then you've got 5 take 3 there. So you get a half times 5 times 2, which is actually just going to give you 5. So yes, this theorem seems to be correct, actually. So we'll go through the induction proof. So the first step is actually just let Pn be the statement. And then we basically got to have this statement here. Convex n-sided polygon has that. So step 1 is actually to prove P3, because that's what we're starting from. 3 rather than the usual spot of 1. So P3 is proven above. So let's assume PK. Convex k-sided polygon has that. All right, so now we're going to be looking at PK plus 1. Now to do our PK plus 1 step, we're actually going to start from the induction step PK. So we're going to be looking at this k-sided polygon here. You can see that it starts here at the vertex I've labeled 1 and sort of works around up to k vertices. And that also means that we'll be having k edges on this polygon. So the way that I'm going to pair up the vertices is sort of by talking about a diagonal like that and calling that diagonal, let's say 1, 3, because it's connecting the vertex 1 and 3. Similarly, we're going to have a diagonal 1, 4, 1, 5. Note that we won't have 1, 2. If I try and draw 1, 2, that's an existing edge on our polygon, so we don't include that as a diagonal. We're going to go all the way down here, and we're going to go all the way up to 1, k take 1. So that would be that diagonal there. Really importantly, we don't include 1, k, because that would be an existing edge already. Now we don't strictly need to do this, but we should think about what the other diagonals might be. So it could be 2, 4 might be one, that would be this diagonal here. And then you could keep going through. So 2, 5, you've got 2, 6, and so on. You could also have 3, 1. Now the thing about 3, 1 though is that we've already got that diagonal. We actually had it already with 1, 3. So I'm actually not going to include 3, 1 here. So we can get rid of that. We do have some diagonals with 3, so 3, 2 won't exist because that's just an edge, neither will 3, 4, but you can sort of start from 3, 5, and then this would go all the way through up to 3, k. I didn't mention before, but this list here also finishes at 2, k. And you can imagine this list expanding out to the right like that. There's a half k, take 3 of these from star. So this is the number of diagonals. There we go. All right. So let's think about doing some surgery on this thing and see if we can add another edge. So the best spot to add it will be here. So I might take that existing edge and I'll sort of cut out that existing edge, and I'm going to be making a new vertex here. We'll call it k+1, and then we'll connect that up. So there we go, that's gone now. So let's think about what new diagonals will be added to our list. So it's all the ones that join into k+1. So there'll be k+1. Now I can't have 1 because that would be an existing edge, but I can have k+1 and 2. I can have k+1 and 3. And I can go all the way up to k+1 and k take 1. So that would be sort of that one there. I've drawn the polygon a little bit weird, but that would be a diagonal. You can't have k+1 with k because that would be an existing edge there. All right, so how many are in this list? Well, we start at 2 and we end at k take 1. That is k take 2. So this is add vertex k+1, and then we might make a little note here, k-sided polygon. All right, so those would be all the diagonals that belong with k+1. Now, if you try to do your induction proof right now, just by sort of adding those together and that together, you'll actually find that it doesn't work algebraically. We are missing one more diagonal. I would highly encourage you to pause the video and try and figure out which diagonal we're missing. And now I'm just going to tell you, we're missing this diagonal here. That used to be an edge on our polygon, but this diagonal right here is now not an edge because we sort of cut out that edge to make it. So we're just going to make a little note, plus one more. So that'll be the one that joins 1 and k. This is now a diagonal. And we are very happy about this because that'll make our induction proof work. So let's look at our total here. I might just give this a few labels. So I might just be like, let's call it A, B, and C, just so we can collect all of our bits. So that would be half k take 3, plus, and then this would be k take 2, and then this would just be the extra 1. Okay, so just to be really, really transparent, that is the existing from star. These ones are the connected to vertex k+1, and this one is the new diagonal between 1 and k. So that's where those 3 bits come from. Now, let's think about what a want to show should look like. So that'll be half. Now, the original statement looks like this thing, half k take 3. So our want to show should be a half k+1 take 3. If you want to simplify that down, it's k+1 with k take 2. All right, now let's do some algebra and see if we can get our left-hand side to look like this. So I might actually just rewrite the same thing out again, just collecting like terms on the end there. And then we can do some expansion. So let's expand the k in first. So we're going to get a half, and then we got k squared take 3k, and then I'm going to be adding on k take 1. We can actually expand the half in. So you get half k squared take 3 halves of k plus k take 1. Might actually write this one as 1.5 just to make the addition look a bit clearer. So you can think about it like with this middle term, you've got minus 1.5 and plus 1. So you're actually going to end up with minus 0.5. Now let's look at our want to show. And the want to show actually does have a factor of a half out the front. So what I'll be doing is pulling out a factor of half here. So half, and then we've got k squared, take k. This should be take 2 now, because if you think about pulling the half back in there, then that would give you the 1 here when you re-expand it. Okay, now there's 2 approaches you can do. You can do the sledgehammer method and expand this. What you will get is k squared take k take 2. But the more elegant method is to sum and product to this. So we've got to think here. What would times to give minus 2 and add to give minus 1? So those 2 numbers are minus 2 and minus 1. So if we look at this, we're going to get k take 1, k take 2, just like that. Sorry, that was my bad. Should be positive 1. That's a little bit nicer. And that does match how I want to show. So what we can do is say, therefore, pk plus 1 is true. And therefore, by induction, a n-sided convex polygon has half n and take 3 diagonals. Wonderful.